Okay guys, in this video I will discuss about the benefit of any box section over the use of I section. Okay, and also you will understand in this video why actually the box section has been generated, though you know that the best section for any beam is the I section. Okay, so if you're new to this channel, please do subscribe and also don't forget to press the bell icon so that in future you can be benefited. Okay, so let's start today's topic. If you are a beginner, in that case, I would like to discuss briefly how does any I section actually act. Okay, and if you are a pro, in that case, you can skip it. Okay, so let's say you have a beam and you have some UDL. Of course, under this load, the beam will bend like this. Okay, and you can draw the bending moment diagram and as well as the shear force diagram for this type of loading and this type of support condition. This is the bending moment diagram and this is the shear force diagram. Okay, we are considering that this beam is subjected to uniformly distributed load. Got it? So you have understood how this beam behave under any type of loading. Okay, now if you consider any particular section, let's say this section. So in this section you will have some bending moment. Okay, and due to this bending moment you will have some stresses across the section. And if you use I section as the beam, in that case the stress distribution looks like this. It varies linearly, and also from this figure it is clear that the majority of the stresses are being carried by these flanges. Okay, so this is the reason it is assumed that the flanges carries the bending moment. Okay, and just like this one, if you consider any other section, let's say this one, and here you consider the shear force. Due to the shear force also, the section will be subjected to some stresses. Okay, and the stress distribution looks like this one. Okay, and here you can see that almost 99% stresses are being carried by this wave only. Okay, so if you are going to use any I section as a beam, then the flanges of the I section carries the bending moment and the wave of the I section carries the shear force. This simple concept will be used further, so please keep remember. Okay, so now we will discuss why the box section is actually required. If the I section is carrying the bending moment through these flanges and the shear forces through its wave, why do we actually need the box section? Okay, let's say this is the beam again, this is the loading, some point load, some UDL load. Okay, and here let's say this is the I section. This beam is nothing but the I section. This is the flange, this is the wave, and this is the bottom flange, right? And this is the support, this is another support. Okay, so you know that due to this external loading it will have some shear force, and due to the shear force stress diagram, you can say if we consider any particular two section, let's say this one and this one. Okay, we can say that the shear stress is actually acting like this one and this one. It will have some complementary forces also, so like this one and this one. So now you can see that this particular zone of the beam is under the action of a resultant tensile force and resultant compressive force, right? So this particular portion of the wave is under the action of compressive load. So if you have any column like this and if you have a compressive load like this, what will happen? Simply it will buckle. Okay, so if this depth is too much, in that case this wave will buckle like this. Okay, so this is the buckling of wave. Why this is buckling? I think you have understood it. Okay, now the question is, what is the solution? How we can resist this buckling, or how we can make this wave stronger under this panel shear action? Simply, if you increase the moment of inertia about this minor axis, okay, so this is the minor axis, about this minor axis the wave is buckling. So if you can increase the moment of inertia about this minor axis, definitely the wave will be strong enough to cater the compressive load. Okay, so let's see how we can make it stronger. Okay, simply we have split the wave in two parts. Okay, and now the compressive load is being applied. Okay, so it tends to buckle about the minor axis, as simple as that. So what we will do, we will simply split the wave and we will put them further. Okay, and we will make a section like this. Okay, many times the beam or the girder are subjected to torsion. Okay, we have some cantilever part and where there is some point load due to this external load. So due to this point load, a torsion is being applied in this beam. Okay, and the practical example of this case is the beam or the girder in the bridges where they are being used in the curve point. Okay, in highway bridges, if there is any curve where you are using this type of girder, definitely you have to design this beam for torsion. Okay, so now what happened under the action of torsion? You know that the farthest point from the CG are being traced at maximum point. Okay, so this point is carrying the maximum stress, this point carries the maximum stress, this point carries the maximum stress, or indirectly you can say definitely throughout the periphery there should be some material to carry the stresses due to torsion. Okay, clear? Great. Now if with respect to this CG I apply some torsion like this, okay, there is no problem in this zone, this zone, this zone. Of course there are sufficient material to carry the stresses. Okay, so there is sufficient material to carry the stresses. But what about in this zone? What about in this zone? There is no such material to carry the stresses due to torsion. So now again, if you simply split the wave and put them further apart like this one, and now if you apply the torsion like this, definitely this point there is some material to carry the stress. In this point the material will carry the stress, and also in this zone, and in this zone, and in this zone, everywhere you will have some material to carry the stresses due to the torsion. So you can say that this shape is much more stable under torsion compared to this one.